This is a continuation of the last video on inverse functions. In the last video, we have talked about inverse function being an undo button of the original function. This is demonstrated by using composition of functions, meaning that if you first do f inverse on x and then take the output and plug it into f, you would get back x itself. Similarly, if you plug in x into f first and then plug in the outputs into f inverse, then the effects of f and f inverse will cancel each other and you're left with x by itself. From here, we see that inverse function switches inputs and outputs. What do I mean? Well, x is the input value to f, and f of x is the output value. Let's call this y. Now, y is the input value into f inverse, and the output of f inverse is x. Hence, you can see that the input into f becomes the output of f inverse, while the input into f inverse is actually the output of f. So we will say that the inverse function switches input and output. And of course, we can also say that the inverse function switches x and y. Because the collection of inputs is called the domain, while the collection of all outputs is called the range, inverse function also switches domain and range from the original function. In the following, we are going to talk about what implications these will bring to us. In the rest of this video, let's assume that f is a one-to-one function, which means that the inverse of f exists. What does it mean by inverse function switches inputs and outputs? Let's say if we have f of 1 equals to -5, then f inverse of -5 would have to be 1 because the inputs and outputs must be switched. If f of 2 is equal to 3, then f inverse of 3 will be 2. If 4, 7 is a point on y equals to f of x, then the point 7, 4 will be on the graph y equals to f inverse of x. Once again, that is because we switch the inputs and outputs. Or you can also think about switching x and y. In fact, this has a wider implication. The graph of y equals to f inverse of x is simply a reflection of the graph y equals to f of x across the line y equals to x. Let's take a look at the following picture. As mentioned in the last slide, if our graph y equals to f of x passes through 1, -5, 2, 3, and 4, 7, then on the graph of f inverse of x, we will have the points -5, 1, 3, 2, and 7, 4. We can see that these 3 points on the graph of the inverse function are the mirror images of these 3 points on the graph of the original function across the line y equals to x. As you can see, this point is a reflection of this. This is a reflection of this, and this is a reflection of this. Furthermore, if this white curve is the graph of the original function, then the graph of the inverse function will be given by the mirror image of this white curve across the yellow line, which is this green curve. So please bear in mind that whenever we are given a graph of a function that passes the horizontal line test, meaning that every horizontal line hits the graph at most once, then we can always draw the graph of the inverse function by simply reflecting it across the line y equals to x. In fact, this reflection across the line y equals to x also explains why we need the horizontal line test. If we have a function whose graph fails the horizontal line test, then after reflecting across the line y equals to x, the new graph will no longer be the graph of a function. As you can see, the same inputs will lead to different outputs. Therefore, in order for the inverse function to exist, the graph of the original function must pass the horizontal line test. After studying how to find the inverse function graphically, we will now focus on finding the inverse function algebraically. There are 4 major steps in this process, where 3 of them are pretty trivial. First, we would like to write down the equation y equals to f of x. For example, if our given function is like this, then our first step is to write down y equals to 3x minus 5 over 2x plus 8. The second step is to switch every single y and x. Why do we need to do that? It is because inverse function switches x and y, and therefore we are going to perform that in this step. And now we will have x equals to 3y minus 5 over 2y plus 8. The third step is the most difficult one. We need to solve for y. Sometimes your equation will have multiple y's, and we first need to collect them together and then make y the subject on one side. In this particular example, we will first multiply 2y plus 8 to the other side to clear the denominator. So we will have x times 2y plus 8 is equal to 3y minus 5. As we said, we would like to collect the y terms, so we will first need to break up the parentheses by distributing x over. So we will get 2xy plus 8x is equal to 3y minus 5. At this stage, many people may get confused, but all we need to remember is our goal is to collect the terms that has y in it. So let's try to move this term to the left-hand side and move this term to the right-hand side. And hence, we will get 2xy minus 3y will be equal to negative 8x minus 5. Collecting the y by factoring it out, we will get 2x minus 3 in the parentheses is now equal to negative 8x minus 5. And the final step is to divide this factor over to the other side, because between this parenthesis and y, it is a multiplication. So y is now equal to negative 8x minus 5 divided by 2x minus 3. And this finishes the third step. The final step is simply to write down f inverse of x. So we will finish this problem by writing down f inverse of x is equal to the fraction negative 8x minus 5 over 2x minus 3. Lastly, I would like to use the previous example to illustrate the property that inverse functions switch the domain and range from the original functions. To begin, Let the domain of the original function be negative infinite to negative 4 union negative 4 to positive infinite. This is the largest possible domain on the real line for this fraction because we have to avoid the denominator being 0. How do we find the range of this function? Instead of finding the range of this function, we are going to find the largest domain for this function. This is from negative infinite to positive 3 over 2 union positive 3 over 2 to infinite. This is because we have to avoid 3 halves in order to make sure that the denominator is non-zero. Hence, the range of the original function will be given by negative infinite to positive 3 over 2 union positive 3 over 2 to positive infinite. As for the range of the inverse function, it will be given by negative infinite to negative 4 union negative 4 to positive infinite. Thank you for watching this video. If you like it, please subscribe to our channel and we will learn more fun math together. Thank you.